Today we're going to start talking about gases and the basics of the properties of gases compared to liquids and solids, and some ways that we can measure gases. You want to stop and pause and write down these notes as you see them on the screen. So let's get started. So we have four variables. The first one that we're going to take a look at is volume. The volume of a mass can be measured in liters or milliliters, or really any unit, but usually liters or milliliters. The unique thing about gases that distinguishes them from liquids or solids is they fill their container. They expand to fill their container. So therefore, the container volume becomes the gas volume. So I've got our little PhET simulation here to show this. If I'm going to pump this little bicycle pump and put a gas sample into the little box, into the tank, and so the gases expand. They have enough kinetic energy that they will always expand to fill their container. And so if we want to know what the volume of the gas sample is, it's the same as the volume of the container. So if it's a 10-liter container, we would say that the volume of the gas is 10 liters. Okay, so that's volume. Temperature. Temperature is a lot of times misunderstood. Temperature, which gets the symbol T, is measured in kelvins. We do sometimes measure in degrees Celsius, but usually for gases, for gas laws, we have to convert to kelvins. And the reason for that is kelvins measure absolute temperature. Well, first of all, let's define temperature. It's an average. It's the average of the kinetic energies of the particles in a sample. So kinetic energy is just velocity and mass together. So if I look at these particles, let's assume they all have the same mass. Let's assume they're all helium atoms inside of a tank here. But they don't have the same velocity, which means they don't have the same kinetic energy, which is why we say that the temperature, and in this case the temperature is 300 kelvins, we say the temperature of a gas sample is an average. So it takes into account the slow-moving ones and the fast-moving ones, and averages them out. It's also kind of gives you an idea, if we think of the definition as being the average kinetic energy of the particles, why the Kelvin scale is best, because the Kelvin scale does not go into negatives. It's absolute. So no matter how cold I make this, it can never go to a negative temperature in Kelvin, because that would be negative kinetic energy. So the formula here for the relationship between the two is degrees Celsius plus 273. So if I say that room temperature is about 25 degrees Celsius usually, you would just add 273 and get 298 kelvins as your room temperature. Okay. The next one, we're not going to talk about this one a lot, at least at first, is we can measure the number of particles. More likely we're going to be referring to moles rather than particles, because the number of particles would be so huge. We will get back to this one a little bit more later and use it in some of our gas laws, but the symbol for it is N. Alright, and then the last property of the four that we want to talk about is pressure. So pressure is defined as force divided by area. We always use the example, if someone has their foot stepped on in a crowded store or something like that, if the person weighs a lot, it's going to hurt. Or if the person has a narrow soled shoe like a high heel, of course it's going to hurt a lot, because the area is so small. So even a person that doesn't apply a lot of force because they don't weigh a lot is going to apply a lot of pressure if they're standing in a high-heeled shoe, because the area, the denominator, is so small. Now with gases, it's usually more useful to think of gases as, or gas pressure I should say, as just the result of all of these thousands and millions and billions of collisions that they have with each other, but also with the walls of their container. So if I look back at my picture here, there is pressure, and it's being read here on this little gauge. There's pressure created because of all of these, hundreds and thousands of collisions. And I could increase my collisions by making the particles move faster. So maybe I heat them up, give them greater kinetic energy, and then you can see the pressure went way up. Okay, I could also increase my pressure by decreasing the space in which they can move. And if I do that, then they're going to have more collisions because they have less room to move around. And so again, you saw the pressure increase. Okay, so that's what pressure is. Now, if we look at how it's measured, it can be measured in a lot of different ways. And you do have to become familiar with these different units. Atmospheres, ATM, pounds per square inch, PSI, which is one that gets used for like car tires and things like that here, at least in this country. Millimeters of mercury, mmHg. I'll get back to that one in a second and where that weird name comes from. And then kilopascals, kPa. Also just plain pascals are sometimes used, but they're so small that we tend to be instead talk about kPa. So those are our 4 units. And honestly, we won't use PSI too much, but I do want you to just kind of be aware of it because it's one that gets used, as I said, in English units. Okay, so here's an important little fact here, and you do have to know these 3 numbers. I notice I didn't highlight the 14.7 psi because again, that's an English unit, and we're not going to concern ourselves too much with it. But I wanted you to have some frame of reference so that when you look at it like how inflated a car tire is supposed to be, you understand about how much pressure that is. So standard atmospheric pressure, or sea level pressure, so a normal day at sea level, where there's plenty of atmosphere pushing down on us. We're almost sea level. I think in St. Louis we're 500 to 600 feet of altitude, which is not a lot of altitude. These numbers would change if you were in Denver quite a bit. They'll only change a little bit for St. Louis though, unless we've got a real change in weather, like a low or high pressure weather system moving in or out. So we can use these numbers and convert between them pretty easily. So let's go ahead and try this one. Using the facts up there, where basically it's telling you that 1 atmosphere is the same thing as 14.7 psi, which is the same as 760 mmHg, which is the same as 101.3 kPa. Can we convert 240 kPa, so the desired inflation level or pressure level for a car tire, can we convert that to atmospheres? So give that a shot right now. Okay, there you can see there the 2.4 atmospheres is my answer. It's actually like 2.36 something, but rounded to 2 sig figs, 2.4 atmospheres, because essentially we're just taking advantage of the fact that 1 atmosphere is equal to 101.3 kPa. So we're dividing 240 by 101.3. We get just a little bit below 2.4, but it rounds to 2.4. Okay. So one last little thing we want to talk about is if you're measuring atmospheric pressure, that is actually done using a barometer, which is an interesting little tool, and we'll talk about why it's important to understand atmospheric pressure a little bit later in the unit. If you take liquid mercury and you fill a tube with it, a glass tube like this one, and then you invert it or flip it upside down into a basin that also has liquid mercury in it, the mercury is so heavy that it's going to drop down a bit inside the tube. It's not all going to flow out, but some of it will flow out because essentially the atmosphere is pushing down on the mercury in the dish, pushing some of it up or supporting some mass of mercury in the column. Now, at sea level, the atmosphere is able to push with enough force to hold 760 millimeters of mercury, hence the name of the unit, mmHg, or millimeters of mercury. But it's able to support 760 millimeters of mercury inside of this glass tube, which of course depends on the thickness of the tube and all that stuff. But that's where the unit comes from. So when the weather changes, if you want to know whether there's rain coming or snow or whatever, if the atmospheric pressure drops, that means that there's less force pushing down on the outside mercury out here, and therefore it'll fall a bit inside the tube, and you might be at 750 millimeters of mercury or 745 millimeters of mercury, and that indicates that there's a pressure drop happening in the atmosphere around us, which usually coincides with a little bit of, like I said, rain or snow or something like that.